Let's take a look at solving a basic exponential equation using the definition of a logarithm. So, for example, if we have 2 to the x equals 3, then the power x is written as log base 2 of 3, which is a perfectly appropriate way to solve for x. Now, oftentimes we want to use logarithms that are base 10 or e because those are most conveniently located on our calculator. So let's look at an alternative approach to solving this equation and see where it leads us. 2 to the x equals 3 is an exponential statement. 2 to the x is a one-to-one function. So it is true that the property of one-to-one functions works both ways, whether you're exponential or whether you're logarithmic. And I can actually say here that log base 10 of one side would have to equal log base 10 of the other side, because 2 to the x is a one-to-one function, and so is log base 10. If I use this tactic to solve the equation, then my properties of logarithms would allow me to pull the exponent down, and I would have x times log base 10 of 2 equals log base 10 of 3, and I'd solve for x as log base 10 of 3 divided by log base 10 of 2. But what I want you to notice is that this must be equivalent to our previous solution, log base 2 of 3. So this gives rise to what we call a change of base formula. So for example, if I were to do this in general, and I could use log of any base, and use the one-to-one property, and using the same technique to solve for x by pulling x down with the rule of logarithms. We end up with the solution for x in terms of some logarithm base c. And so we end up with the quotient log base c of b divided by log base c of a. But we know if we had gone directly from the definition of the logarithm from here, then x would be log base a of b. And so this is what we call a change of base formula. Okay, now how will you apply it? Well, there's a variety of problems. I mean, certainly you can always, in solving an exponential equation, use the base that you have on hand and then convert to another calculator type base using the change of base formula. But let me show you just a basic example. So for instance, if I have log base 5 of the number 12, and I know that on my calculator are buttons for log base 10 or log base e, and let's just say I want to use log base 10, could equivalently, and I'll just write that here, use log base e, okay? But the change of base formula says this to me. When I look at this process, I have log base 5 of 12. So when I convert to a new base, notice where the values go in the new formula. So it's log base 10 of 12 over log base 10 of 5, or natural log of 12 over natural log of 5. Or if I do the calculation for either one of these, you will see that you get 1.54395 and some change, okay, which you could then round to 4 decimal places from there. Okay, so here's a slightly different twist on the change of base formula. It says evaluate using the change of base formula without a calculator. And what you have is log base 5 of 64 divided by log base 5 of 8. And yes, you can see the log base 5 is common to each. However, what you're looking for is an ability to convert to something that you could calculate the logarithm of 64 and the logarithm of 8 without a calculator. And both basically 64 and 8 are divisible by 8. So ask yourself the question, is 64 also a power of 8? And the answer is yes, since 64 is 8 squared. So what if I use the change of base formula and change how both the numerator and the denominator of the existing fraction look by using change of base to convert to log base 8? So log base 5 of 64 would convert to log base 8 of 64 divided by log base 8 of 5. And log base 5 of 8 would convert to log base 8 of 8 divided also by log base 8 of 5. Your algebra rules support that these two cancel each other out. And you're left with the quotient log base 8 of 64 divided by log base 8 of 8, and we can calculate these without a calculator because we know that 8 squared is 64 and 8 to the first is 8. So it's a different look at the change of base formula.